Thank you, Carlos, for an introduction, and thank you to all the organizers for having me here. It's an amazing workshop. And mostly thanks for the opportunity to give the speech right after lunch. So it's nice. I hope you are all awake because it will be really interactive. And I am really looking forward to your questions. So please don't be shy. Just raise your hand, interrupt me, and it's everything fine. It's what we are looking for, to learn all together about this fantastic tool. But let's start with the topic of today. Who of you, please raise your hand, knows about the global natural product social molecular networking? Many of you? If someone doesn't know, it's normal. It's normal because it's well known as GMPS, as all of us know it. And today we are here because I want to introduce you. This is the GMPS1, basically, ecosystem. This is what, if you log on GMPS1, you will find this. But as I told you, GMPS2 has been created, and so the developer did a great work to create this GMPS2. And so today I want to introduce you to the feature-based molecular networking on this new platform. So I think all of you got the token from Carlos. There is someone who couldn't log in or had some problem doing it? Okay, great. So please, I would like you to log in your GMPS2 account. Are you in? Great. Okay. Huh? Yeah. Did you set up everything? Someone have problem in doing that? No? Okay. Don't be shy. Don't be shy. Just interrupt me if you have some kind of issues. Okay. What now we have to do is to upload our file, our data that Stefan produced through the MZMine software on our GNPS basically folder. But before we have to create a folder. So I would like you to click here and to create a folder with your name. There's someone who already did it. Okay. Yeah.
Just like make sure that
yeah. Yeah.
So for those of you created an account already with the tokens that we provided you. Okay.
Yeah.
And then log in now.
Great.
And then you're all ready to upload your files.
Okay. Okay, great. So what we basically have to do you have your file on your PC? Raise your hand if you have your file on your PC. Okay, they're not that heavy, so if you don't have on your PC, you can download them very easily. Please do it, and you can basically just drag and drop them on the folder that you create, and you should see something like this afterwards. So you have these 3 files, the MGF file that just a small recap, but just to introduce it. The MGF file, which is the MS data file. We have the additional edge annotation. I will go through this in a second. And the quantification table. So we have to drop them into our folder. Yeah. Yeah, okay. I thought everyone had files downloaded on his PC, but otherwise, you all have access to the shared folder on Drive, right? Let's go. Here we have. Yep. We have this file here. In the MZMine tree folder, we have this file, which is the quantification table. Yeah. In the export reprocessed data folder. Did I? Yes. If you find any problem, just tell me, and I will stop and I will repeat it. Then we have the annotation, the edges annotation file should be a CSV file as well. Do you all have it? And then we have the MGF file, which contains all the information, MS1 and MS2 information we need, of course, for the molecular networking. So please download these 3 files. There should be also the metadata. Yeah. In the MZ-Mine3 folder, we also have the metadata. As you know, we want to give like our tool a way to group like data based on some attributes that we give into the metadata. We'll go through it in a second. But so we need also this metadata table TSV file to be dropped in our folder. Any issue? Raise your hand if you have an issue at this step. It's very important that we have all our data into the folder. This is a TSV. Yep, please. Yep. Yes. Actually, I can do better. We can do it together. So I can create with you another. Okay. 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 Okay, I'm creating a new folder. Just yes. Okay. Okay. File browser. Sorry. Yes, sir. Here we are. Click on file browser. Everyone is in file browser? Yeah. Better? Great. Now we can create, oh, sorry, this is a new file, a new folder here for those who don't have it. Great. So this means fill flawless. So we have to fill this folder with our data. So we just take our data from our folder. The MGF, the MS annotation, the quantification, and the metadata. And we just release them. We drop them into the folder. So now when you see them, they are in. They are there and they are available to be used. Okay? Any issue on this step? Okay. This is just to make like the platform available, the data available on the platform, of course, because otherwise we cannot use them. If you want to use the raw data in the same way, you can drag and drop the raw data. You can also do that. Of course, it will take more time. I did it. It will take more time, but you don't have to use like WinCP or this kind of things. So it's a bit more immediate. I don't know which is the capability of this, but I did with the raw data from this workshop and it worked. It took like a bit. And yeah, that's something that you can ask like also to Ming. But it's something really useful. I found really useful. Yes. No, okay, no, you have to use the simple one, not the full one. The full one, okay, I think this can answer better, Stefan, but the full one contains way more information that are not only needed, but that can like make your work fail. Actually, it contains way more information than we need for doing the molecular network. Yeah. There is someone who still needs some time to do it. Just raise your hand, no problem, just to understand when I can go. Yes. Yes. We have a question there? No, no. I think in the future you will do your own account very easily, but now it's still not available in this form. Yeah. So you need the token to have an account right now.
Right.
Yeah.
But then at some point, you opened up, and you have collaborators that need one, they can do it anyway. But you the main developer, I have some blue things.
Everyone is in? Okay, great. So we can go with our actual workflow. So what we want to do today is a feature-based molecular networking. And in a while, I will tell you which is the difference with the classical molecular networking for those who already did it, and so on. So at the moment, we are just starting our job because it will take some time. Actually, it took like 50 minutes for me. So it's better that we start as soon as possible. So what we can do is to go on workflow. You just click on that. And here you have search bar. And since there are, as you can see, many, at least 44 different workflows, we have to look for ours. The faster way, of course, is to look for it here. So I will just type feature, and here we are. We can click on launch workflow. I do it. Okay, and here we are. Here we can type our job description. So just type something that would allow you to recognize the job you're running right now. Here. Like this. Then we click here on one of those green buttons, and now is the moment to import all the data that we download. So we click on our folder. Now this is mine, you have yours, you give your own name to the folder, and so you double click. Here, my actual folder where the file are is this one. So basically I can import. To import, you just click on, for example, here we have the MGF file. Who does know what the MGF file contains, where we should put it? Like here we have input features, input spectra, metadata. What does the MGF file contains? Someone knows? Spectra, great. So we just click on input spectra, okay? Then we do the same with the edge MS annotation. Who knows? What does it contain? This is a kind of a new feature. Yep. The edge annotation contains like, yeah, it's very useful for the ion identity. It's like it's a new MS1 layer of features of edges. So it's useful to see which multiple adducts one single feature has. So this contains this kind of information. Then we will visualize it in Cytoscape. So don't worry if you cannot see in your mind what is that, but we will see it. So you have to click here with this, and you have to import in supplemental edges file. Okay, should be. loaded. And then we have finally the quantification table. Where do we have to put it? Someone knows? You heard of it for sure? Okay, great. We have to put in features. Now we can close it. Okay, no, before closing it, we have also the metadata that we have to import. It for a reason is not there. Okay, it's here. I have it in another folder, but you have in your own folder. So what we have to do is also to import the metadata. You click on metadata the same way. Yes, we have a question there. Yeah. Yes. Yes. Yeah. Yeah. Yes. Yes. That's a great question. Okay, I'm gonna introduce later. So I'm gonna just tell you which is the minimum requirements for a metadata. The metadata is optional, as we already said, but it's nice to have a grouping, a way to group your features for your own research purpose. So what we're gonna do is to import the metadata here. And then we can close. Is everyone with me? Okay. Okay. Which is the problem? Which is the problem? Did you? Yes, we have a question here. Okay. Feature-based molecular network. Yeah. Do you have raise your hand if you had some problems in uploading some files? Okay, which problem do you have? Which? Okay, I can repeat it. The MGF file, are you here? Are you in this screen? Do you have the screen in front of you? Okay, let's take the MGF file. The extension is MGF. Yeah. The MGF goes in input spectra. Great. Are you all done with this, the MGF? Okay, great. The edges, don't tick both of them, otherwise you will get both of them into the as input. So the MS annotation, this one, CSV file, goes in supplemental edges file, this one. Raise your hand if you are not done with that. Okay. We untick it and we tick this one. This is the quantification table. So we put it as input feature. Done? Great. Then for the metadata, we import, of course, in the metadata. So here. Okay. I think everything is done now, right? Great. Okay. Now, if everything is done properly, you will have here input features and you will see the file that you imported. So if you do something wrong, you can still correct it at this point. You will double check it. So you have the quantification table as input features. That's correct. We have the input spectra and we have the MGF file. That's correct. So we have the metadata in the metadata. So that's correct. The library, this is something that is always there. You can, of course, you can provide more libraries. You can do many things if you have it, but this is like the MGF library and is of default. And here we have the, okay, the edge, the additional edge file and this here. Okay, so that's correct. Now, yes. Of which one? Okay, this is like something that was born for with the ion identity molecular networking. So it's something, it's to add like additional MS1 information, like different adducts for the same features. Like in here, there are the connection like of M plus, if you have like a feature in which you recorded the M plus H, In here, if you add this, you have also the information about the N plus sodium, the N plus potassium, the N plus ammonia, whether they are there. So, yeah. Yes, 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 yes. All these files, apart from the metadata, are like done through MZMine. Now, here we have the ion tolerance. Since we are using a high resolution MS, you know which kind of like tolerance. You think this tolerance is good? Why is not good? Tell me. It's too big. Because we are using an high resolution with this tolerance, we are gonna get like 2 delta, also different molecules from the molecules that we are doing. Then usually, typically we use 002, like to don't be too strict, but not to be like. Then I use this one also for the fragment ion tolerance, because this is for the precursor ion, and this is for the fragments. Since we're using a high resolution, we can use the same. Now we have the minimum peak intensity. I think that since we processed all the data with MZMine, I think we don't need to add a different threshold in this case. So we just put it to 0 because we already processed all the data and we already cleaned all the data with MZMine, as Stefan showed us. These parameters are like to make the fragmentation spectra cleaner, because sometimes, especially with cutoff instrument, you can have some issues around the precursor ion spectra. So usually I would suggest you to filter, to always like put on yes these 2 filters. They are very useful. And it comes to the networking parameters. You already heard of it. You already heard of the cosine score. So you know that this cosine score is the score that allows you to network different molecules. Who can tell me what happens if I increase this score like to 0.8 or 0.9? Yes, this is from 0 to 1, correct. So yeah, that's correct. If we increase it, of course, we are gonna get less molecules correlating to each other because we are very strict with the parameters. So 0.7 is a kind of a parameter that allows us to have like a good networking, but also a trustful networking. So we can trust that those molecules that are correlating with each other are really similar, structurally similar. Then, as these are the minimum amount of peaks that have to match between the 2 fragmentation spectra to be in order to be correlated with each other. Okay, so we want that at least 6 fragments match with each other in order to be correlated into the networking. And then this is okay. This is like a maximum shift between the 2 molecules, the 2 precursor mass. Everything fine with that? Raise your hand if you don't understand something. I will stop. Now let's go to the library search parameters. This is also.
Is the number of match peaks, is it generally applicable? So should you always put 6 there, or do you have to change it sometimes?
That's correct. It depends from the kind of molecules you're looking for. Of course, if you have molecules that fragment really well, it's very likely that you have many peaks. So it's useful to have like a higher number of peaks that have to match in order to be connected. But if you have molecules that don't fragment so much, you're not gonna get any networking because you don't have 6 fragments that match with each other. So that's a really good observation from Stefan, and it's a great point. Let's go ahead with the library. Here we have, okay, yes. As before, we have the cosine score, and this is basically the same. This is the cosine score that you have to between your carry molecule and a library match in order to be matched with each other. So we always use 0.7, as I said, is a trustful parameter. You can also increase it, but I would never decrease it, honestly. As before, we have the minimum match peaks. It has to be 6 in order to be matched with a library hit. And in this case, I'm not performing the analog search. The analog search basically serves to allow your carry molecule to cluster also with another molecule, which is not that one, but we share chemical similarity, so fragmentation similarity, okay? So when you have a library hit, it's because your precursor ion and your library hit, they have the same precursor mass, okay? Instead, with analog search, you can avoid this, and you can get like library hit analogs hit also if your precursor ion and your analogs, they don't have the same mass, okay? But I'm gonna avoid it because it's very heavy, and for our purpose is not useful at the moment. At the top, okay, this is the top. It's like that you can have for each query molecule. Okay, for now it's one. Okay, I will skip this, the normalization parameters, and we can just submit our workflow. Is everything fine with all the data? Do you want me to come back to recheck all the data?
Also, maybe just to calm you if you did not make it to that point, Giovanni has a already finished job that he can share with you in a second, and you can build up from there. And that's first of all to like kind of like take you all with us to like the next step, but also we're not hitting all the server at the same time. Because if you know 60 people simultaneously hit the server, it's interesting performances. So don't worry if you cannot also. If you have it ready, feel free to go ahead, or later, you know, during the workshop, it would be great if you get your own first job in the user console. In a second, Giovanni has to share with you. From there.
Thanks, Daniel. Yes, that's true. Here you can see in the Eco-Metabolomics shared folder, you can see this file, this Word file, and in here you have the link. There is only the link that you have to paste in your bar to have the job I run. This one. You just take it. Yes. You just paste it. And here we are.
Basically, if you had submitted the job, if you would have waited for like half an hour or something, you would have gotten an email, and then it gives you a link, and then you can go to this website. And in your primary level GMPS1, it's very much the same concept. You get this URL, put them in your paper, or you can like share them with your collaborators, and then you kind of like can reproduce like whatever data analysis comes out.
Thanks, Daniel. Yes, this is like when the work is done, as Daniel said, you will see the status done. And while now, if you run your job, don't do it all together as Daniel suggested, but later do it because I want to see, and tell me if it fails. Just send me, we will see each other tomorrow. So tell me if it fails, and we will try to troubleshoot it, because it's important that all of you are able to run it even without us. And so here, if whenever you run, you will see running. And yeah, we will go through the results later. I just want to give you like some background on the difference between classic molecular networking and feature-based molecular networking. So before analyzing the results, so don't close this page. Don't close this page. I go back to the presentation. We did all of this. We did all of this stuff. So, well, this is the link. Presentation mode? Yeah. Okay. Yeah. To do that. Yeah. Okay. Okay. If it works, it would be nice. Okay, you probably already saw this slide, but it's important at this step. If I know that there are some people already doing these experiments, already running their LCMS run, but I also know that there are some people don't do that. So I want you to just stop me if you don't understand something. Well, when we analyze complex samples like in ecology and in eco-metabolomics, we do our eco-metabolomics studies. So of course, we have really complex samples. So the first step of every good analysis, and I hope you really take care of this step because it's very important, is the chromatography. So to choose the best chromatographic way to separate molecules, because we have really complex samples, and for our MS detector, it's really hard to understand and to give us all the information from a really complex package of molecules. So the first step is this one, is the chromatographic separation. So when molecules are separated, we use different ion sources. I won't go through that because Allegra already did it in the different ion sources that are available. Basically, what we do here is to ionize molecules and to have them charged in order to be analyzed, because that's really important. We are not analyzing the molecule itself, but some adducts, which can be the protonated adducts, the sodium adducts, and potassium adducts, and so on. And so they fly to our MS detector, and then finally, hopefully, they are analyzed through our high resolution MS detector, and through the Fourier transformation, we obtain what we call a mass spectrum. But what happens in the between? I mean, how we can get the MS2 data of these molecules? Basically, we have a duty cycle. So this cutting edge detector are able basically to record MS1, and we can decide through by setting different parameters how many of the most abundant ions for duty cycle, we want to fragment. So you can fragment the top 3, the top 5, the top 10. There is not the best parameter, as you already learned from Stefan and from Allegra, but of course it depends from what you're looking for. So the top N ions are fragmented, and of those, we also have the MS2, so the fragmentation of those. But now, who can answer this? What an MS analysis can tell us about a single molecule? What we can learn about the molecule? Do you have an idea? If you don't know what you are like infusing, what we can learn from an MS analysis? What? The weight. The weight, the molecular weight. And what does it tell us, the molecular weight? We are just like putting this molecule MZ on a balance, and we know the weight. So what are we learning about that molecule? Who said it? Great. The formula. So we can have an idea, if we have a high resolution MS, we can have an idea of, from this number, because it's just a number, it's just a weight. We can have an idea, if we have a high resolution MS, we can have an idea of the possible formula. You don't have one formula. You can have like a restricted number of formulas. But if you have a low resolution MS, you have hundreds and hundreds of formulas, possible formulas. So you are not gonna have this information. So that's cool. And what we typically do, as I said, is like to destroy this molecule, because we want to learn more than only the formula, because this doesn't tell us three-dimensional disposition of the atoms. This doesn't tell us how these atoms are binded with each other. So we just like destroy the molecule, and we obtain like MS2 spectrum, which is like, let's say, a fingerprint of that molecule. What we can understand from the MS2 spectrum, which are the information. Why do we that? Here we have connectivity as answer, substructure. To confirm that, if it's untargeted, so you don't know anything about that metabolites. Yeah. It's you're perfect. You're right. If you are doing like targeted analysis and you want to confirm, and you can just compare the fragmentation spectra, and if you have a very good match, you have a level 2 annotation, which is important and which give you an information. All those answers are correct actually, because what we have is an idea of the substructures. And so thanks to this one, we can perform, as we saw today, molecular networking. So we can connect them basically based on the similarity between the fragmentation spectra, which is translated in a similarity in the structures. So this is the correlation. This is the important thing. So, and also this allows other tools like we will learn by Marcus, like Sirius, to do a chemical classification, because of course, if this is a fingerprint, the fingerprint will tell us also which kind of molecule families has that kind of fragmentation spectrum. And in the best cases, there is like a tool recently released. We can also do de novo structural elucidation from the fragmentation spectrum. So we can basically predict the structure ex novo of a molecule. But let's go back. What molecular networking does? Basically, molecular networking couple all the spectra based on their similarity, as we already learned, and based on that, establish like based on the cosine score relationship between them, couple them, and yes, this is a very quick explanation. I will skip about the cosine score because we don't want to go really into it. But basically, if you have a cosine score of 1, those are like identical, that's not similar. And if you have a cosine score of 0, they are different. So this is what we have to get in mind. That's why we use 0.7, because we don't want to be too strict, but we don't want to be like that, like 0. And so basically, when we have this spectra, what molecular networking does is to show some nice nodes for each spectra instead of like the spectrum that would be crazy to visualize, and with some mass Z ratio for all of them, and connect them in a very nice visualization, because we can analyze our data, but then also the visualization is important, because if we have to go through really complex data, it's going to be really hard. So this is like an example of a small molecular network. So we have these nodes that are similar to each other, and these two that are dissimilar from this, but are similar with each other. And hopefully, if we are lucky and we get an ID, like in this case, we are going to have information not only on this guy, but also on the connected nodes. Because if we know that these nodes, we have a library ID, and as he said, we have a perfect match. We are lucky we have a perfect match. From the difference from these nodes, we can also try to understand which kind of molecules here we have. So we started that we didn't know anything, and now we know 3 molecules ID. That's the important thing of molecular networking. Okay, now what to understand what we're gonna watch in a minute, like on Cytoscape, it's important to just stress this thing that Stefan already explained very well in the previous talk. Basically, we started from raw data, and we built some chromatograms, and we did a lot of filtering steps and also of isotope grouping in order to reduce the complexity of our data, because we, as you saw, we have very complex data. We can automatically detect isotopes and filter out them. We can automatically detect with the ion identity molecular networking workflow, we can automatically detect different adducts of the same species. And finally, we can arrive to our output that we just submitted to GMPS2. But of course, instead of doing this manually, as I used to do before, you can save your processing batch, and you can repeat it, and you can let these guys do it for you next time. So whenever you run all your data in the same condition and on the same MS instrument, it's more practical to save it as in batch mode than to repeat it next time. So just to stress, for last time, what we are doing basically is we are analyzing. We are analyzing our data-dependent analysis data, and for each mass, we can build an extracted chromatogram. And so for every precursor ion, we can perform some fragmentation and experiments that are represented by the stars. And finally, we align across different samples all the features, and we have like a situation like this in which these metabolites was detected among different samples. Here we have the correlation, we speak before. Basically, this is like the ion identity, molecular networking, important parameters, because this allows us to correlate all the different adducts of the same metabolites. But I will skip it because it's maybe easier to show you what I'm talking about. Basically, in the ion identity networking, we have these metabolites here, let's say the M+H, and you can automatically detect just by the delta mass between the M+H and the M+ ammonia or the others. You can detect all the others ions. And instead of having like something like that, you can also have something like that in which you have many ions of the same molecule. So in this way, you are also reducing the complexity, because you won't go to analyze all those nodes, because all those nodes come from the same chemical species. Yeah, here you will have the presentation, so you can find these important papers about the feature-based molecular networking. And yeah, coming to us, which is the difference between the classic molecular networking and the feature-based molecular networking. Imagine that we have these two samples with these 3 peaks, okay? Sample A and sample B. And in this case, in sample B, this peak was not fragmented because it was under the threshold, or because it was polluting with many other molecules. So we didn't have the chance to have the fragmentation spectrum of this. So if we perform a molecular networking, a classic one, we don't have basically any feature about this peak. But if we perform like a feature-based molecular networking, which is this one, this will be detected, because the peak area will be detected. It will be included in the quantification table. So we will have information about the relative quantification of this peak in our data. Yeah, I think we can skip this. Okay, so how can molecular networking help with the annotation issue? Because you must know that this is like more or less the size of the spectral libraries, fragmentation spectral libraries that we have available today. There are also some structure libraries, so not fragmentation spectra, but molecule structure libraries like PubChem. Have you ever used PubChem? I guess so. Raise your hand if you use PubChem. Okay, I was expecting more. And PubChem is basically just like a repository of molecule structures. And they are bigger, the structure repository are bigger, but the reality is that compared with the chemical diversity that we live in, those are 2 dots. So we don't know anything yet about the world. But if we are able to network similar molecules among them, this is the result that we can obtain. So we can constrain this chemical space by networking similar molecules between each other. And we can learn more about neighbors of molecules which we know the identity. So this is really important. We can constrict this chemical diversity. And you will learn this from series from Marcus, but we can also predict the chemical class of those molecules, just having this fragmentation spectra. Now I will show you just some of the feature-based molecular networking applications that are actually available. Of course, it's really widely used in the microbiology and the natural products field, from which I come from, and in ecology, in medicine, and where basically you obtain these very complex data, and of course you try to figure out what does change in different conditions, and with all the
the profiles, it's really complex. You have to find, okay, this peak is here, but it's not there. It's kind of tricky. It's kind of hard to do it manually. So we need some tool. With the molecular networking, basically, you can do it, and you can see if one feature, which is one node, one molecule, is in a sample and is not in the other sample. And as I said, you can perform chemoinformatics analysis and statistics, as you learned from Jos. Now I will show you just a small example of a study I conducted in the past years. Basically, we had this deep sea bacteria, and it was really nice because there were not secondary metabolites annotated from this genus, and so we were really interested into it. And basically, we didn't find anything in the genome. We sequenced the genome, and we couldn't find any interesting biosynthetic gene cluster. But we found weird things, that this bacterial genome contains like a tryptophan decarboxylase, which is a gene contained in plants. It's very frequent in plants, but it's not that frequent in bacteria, which is used to produce tryptamine, which is a neurotransmitter. And this gene is also really present in our body, but not at all in the deep sea bacteria. So we try to understand which is the meaning of doing it. Why do you have this gene? So we got in mind that following the Le Chatelier principle, we could basically try to feed it with tryptophan to try to move the equilibrium of this reaction, because we didn't know the rest of the path. So the only thing to try was this one. So basically, what we tried, we did 3 conditions, of course, with all the replicates. And basically, in one condition, there was like the normal media. We cultivated the strain in the normal media. In the second condition, we added tryptophan, which is like a nitrogen complex source. In the third case, only in the third case, we added tryptophan. We performed untargeted molecular networking and chemoinformatic analysis, and what we got is something like that. And these 2 big molecular networks were present only in this condition. And through like a biutilizing series, we got in mind, we learned this basically, as you can see from the colors, the red ones and the orange ones are alkaloids and indoles and derivatives. So they all come from tryptophan, basically. So we were really happy to find serotonin and other tryptamines, which are neurotransmitter, and they don't have any meaning in deep sea, actually, as we know, of course. So through this, we found that thanks to the molecular networking, the feeder-based molecular networking, we found that basically the common fragment among all of those was this one, like a tryptamine moiety, and we were able to isolate for the first time these metabolites, and the first metabolites from this strain. Okay. Yes. Some question? Just stop me if you have some question. Okay. Maybe we can stop for the break, and then I can go ahead with going through the GIPS2 data. Are you fine with that? We have a question.
I was working on the subsurface protein.
Yeah.
So we got some bunch of metabolites from the subsurface samples.
Yeah.
But we could not find in literature what is the role. So then people are telling that to remove it, may be kind of contamination and something. So because now you have shown this bacteria which is from the sediments, and you got this metabolite which can be has a relation to tryptamine, and then serotonin, all these metabolites. Can you say how can you prove that these metabolites are from that kind of environment and they are producing this kind of metabolites in that environment?
Okay. If they are producing the environment?
Yeah, so I got this some kinds of metabolites from the subsurface samples, which does not have any role in the deep subsurface.
Yeah.
But we got some metabolites, so we have to remove maybe it's a contamination during processing, because we know deep subsurface samples are very low in biomass. So it can be also contamination while processing and stuff.
Well, in this case, it's not because this is like a pure culture.
Yeah, this is the
but in that case, I mean, if you're analyzing just you never know. I mean, it's a really complex system. the deep sea is really, you know, all the DOM question and things. So there is a lot of refractory molecules that you don't know how they reach space. So I don't think it's like there is not like parallelism between the two situations. So to understand like a deep sea, of course, the best thing is to study it in locus. So to study the system where is, but yeah, I mean, it's hard to predict the meaning of such a method. To understand. Yeah, they can do it. They can do it. It's not doesn't mean that they do it in the deep sea.
Yeah, that's the thing.
Yeah.
So they can do this metabolism in their inner culture.
Yeah.
So do you know does similar kinds of metabolism and metabolism in the organic?
Yeah, and I don't know, but a cool experiment that could be done like is to extract like the DOM of like a deep sea or deep sea where the bacterium was collected, which is in Antarctica, and to feed the bacterium with that kind of extract. This can be something, and to see if like some of these molecules pop up.
Okay.
This can be like an experiment that can be done, but it's a really good point. Okay, so we can have where? Oh, here. Sorry. Yeah.
Yeah.
Yeah, I think this is a question that you can ask for to serious people like to Marcus, and yeah, they will know better. Yeah. Ah, yes. Sorry. She asked about MS Novalis, so about the novel structure elucidation from fragmentation spectra, and basically this is a tool made within Sirius platform, so you can ask Marcus, and I'm sure that you can tell more. I've never used it. Any more questions? Okay, so we can have break.
Yeah. Okay. So welcome to coffee break. Let's take half an hour. The rest of the day, and then we come for the next session.